I will sort of start at the beginning. I just want to say I have to apologize for a bit of false advertising, because I said I was going to talk about two things. Machine learning for understanding glassy dynamics, and then persistent homology, methods for looking at design functions. And in putting this together the last few days, I realized that the machine learning for glassy dynamics really was enough to fill the time. And so tomorrow I will be talking about how to design networks and then study function in those networks using persistent homology. Okay, so all right, so what is the goal? So I'm going to talk about using machine learning, and in the course of doing that, I'll talk about various machine learning approaches, okay? But I'm going to do it in a specific context, okay? And that is learning new physics from it, okay? And what do I mean by that? So I'm a condensed matter physicist, and the goal of condensed matter physics is really to understand collective phenomena, many body phenomena in many body systems, okay? When many things are interacting together, but to understand that from the microscopics, okay? So to have a microscopic understanding of these collective phenomena. And basically, when you think about that, if you start with the microscopic information, that's way, way too much information. So we have the too much information problem, okay? And somehow, right, what statistical mechanics does for us is to boil down all that information about the microscopics into what are the most essential things that we need in order to understand the collective phenomena that we're interested in. Okay, and and basically the idea is you use this microscopic information. For example, you have a classical system. All the systems I'm going to talk about are classical. So then we have the phase space variables, right? The positions and momenta of all the particles. That's a lot of information, okay? And of course, the interactions between the particles. And what statistical mechanics says, oh no, what you want are to look at averages and variances of, whatever quantity you're looking at. So if you have the Ising model, you would be looking at the average magnetization. You'd be looking at the susceptibility, which is related to the variance of that magnetization, for example, okay? And so statistical mechanics has just been fantastically successful for more than 100 years in bridging from the microscopic level to the macroscopic level and solving this, too much information problem. But we are interested in problems where statistical mechanics fails, okay? And there are various reasons why it can fail. I'm going to talk about one. I'm going to focus on one, which is the glass transition. So you could, at the microscopic scale, you start out with atoms or molecules, right? You can have a molten glass. It's a liquid, okay? Or you can have solid glass. That's what we're used to, right? That's acting like a solid. And the transition between these two is not very well understood. Actually, just in the last 5 years or so, this problem has been solved in infinite dimensions, okay? So that is great. You can use statistical mechanics in infinite dimensions, okay? But we have not been able to go from infinite dimensions down to 3 dimensions, okay? And so we still do not have, statistical mechanics has still not enabled us to understand what's actually going on in the dimension that we live in. By the way, these are glass vessels from 1500 BC. So we have been using glasses for a very, very long time without actually understanding how they become glasses. Another example, these are examples that I have been sort of obsessed with for 20 years. Okay, so I'm just talking about, you can have individual sand grains. You can know a lot about them. Often people in the lab just use spherical glass beads, okay, characterized by some friction and so forth. But these, we know that sand can be poured like a liquid. It can behave like a liquid. Or if you walk on a beach, you don't sink through it. It supports your weight, okay? So it's acting like a solid, okay? And so sand can undergo something not entirely dissimilar from this. And of course, we can start with, we can look at shaving cream, which, if you think about it, it's made out of bubbles. Okay, we know a lot about soap bubbles, right? But you put them together, you can smear it around, so it behaves like a liquid, okay? Or if you just put it on your hand and you just jiggle it, right? It doesn't flow away. It stays on your hand, it holds its shape, it's acting like a solid, okay? And so these are all sort of systems that, you know, we've thought a lot about. And, you know, what characterizes all of them is that they are far out of equilibrium, right? Statistical mechanics is really for systems that are in equilibrium or near equilibrium. These systems are far out of equilibrium, and so they pose a real challenge. They are disordered, they're lacking symmetries. It's not like we have a lattice, a periodic lattice, and we can use lattice symmetry to help us. We don't have that. And they can have nonlinear responses, right? If you take a foam, you push on it gently, it behaves like solid. You push too hard, right, it flows like a liquid. So that's a nonlinear response. And all three of these things, any one of these three is really enough to cause trouble, okay? These systems happen to have all of these three problems, okay? So, as I said, what we have is really a too much information problem. And that's exactly what machine learning is designed to do. You start out with lots and lots of data, and you boil it down to what's important, right? You see images of many, many, many cats, many, many, many dogs, right? Machine learning can sort them. This is a cat, that's a dog. That's a huge reduction of dimensionality to go from all of those images with all these differences between all the different cats, right? And just say, that's a cat, okay? So this is what machine learning is for, really, is for reducing the dimension down to a small number. And so it's a natural to think about machine learning for this problem, but the question is, how can we use it to bridge between the microscopic scale and the macroscopic collective behavior in a many-body system? How can we do that? And moreover, the ultimate goal, right, is to use machine learning as a basis for developing theory. As a physicist, that's what we want to do. And that's what my focus is going to be on. There's been a huge amount on machine learning, applications of machine learning in physics. You know, you can do electronic structure with it. You can tell whether you've got two circular galaxies that are close together or one elliptical galaxy, or if you have a picture, an image of a tissue, you can say, aha, that's the cell, right? You can use it to distinguish individual cells and so forth. So it's great for these sorts of things, but what I'm talking about is different. I'm talking about using it as a tool to bridge from the microscopic to the macroscopic scale, and as a tool for theory. So the stuff I'm going to talk about, I'm going to focus mainly on this, machine learning as a way to get microscopic insight into glassy dynamics. I've been collaborating with a lot of people on this. This was really started out by two graduate students, Sam Schoenholtz and Dosh Chubuk, who they were friends as undergraduates at Swarthmore College, and then Dosh went to Harvard to work with Tim Kaxiris, okay? And they were using machine learning to do electronic structure, okay? And my graduate student, Sam, was interested in this glassy dynamics problem, okay? And Sam went to visit Dosh, and they started talking about, telling each other what they were doing. And Sam said, oh, I wonder if machine learning could be useful for glassy dynamics. And they did it. They actually applied it, and his job was to find, is there a local structural signature, is there a structural signature that will tell me whether a particle is likely to rearrange or not? And they actually did it, and they got 90% prediction accuracy before they even told me anything, okay? So they really deserve a huge amount of credit for this. Then later, a postdoc Diana Sussman, and most recently, François Land and Giulio Biroli, Olivier Dochot, David Reichman I'll show you a little bit of that. But the original work was done with, also with Doug Durian and Jörg Rottler. Okay, the original application of this. Okay. So what's the glass transition? Let me start by telling you what it is, okay? So if you take any liquid, okay, and you cool it down slowly enough so that there's no time for it to crystallize, the little crystals to nucleate and grow, okay? Then, you cool it fast enough so there's no time for this to happen. What you'll get is a glass transition. Any liquid, this is generic. Okay, you just cool it fast enough so that there's no time to crystallize, you will get a glass transition. And what happens as you go through this glass transition is that the particles remain in a disordered configuration, as in the liquid, and the stress relaxation time increases continuously. So what do I mean by that? I'm going to call that tau alpha, okay? And it's the time for the system to reach equilibrium. It's called stress relaxation because what's the difference between a liquid and a solid, right? If I take a solid and I put a stress on it, okay, it'll push back. It'll cost me something to hold it there, okay? It'll cost me energy to hold it at this strain. If I do this to a liquid, initially, it will cost me something to hold it at this strain. But then what happens is that the particles rearrange their positions. They change their neighbors, which does not happen in a solid, okay? In a liquid, they can change their neighbors, and that relaxes the stress, okay? So in the end, it doesn't cost me anything to hold it here. And that time scale for it to cross over from a solid-like response to a liquid-like response is the stress relaxation time, okay? So if you take something like water, it has a very short stress relaxation time at room temperature, like on the scale of picoseconds. But if you take honey, okay, it's much more viscous. It has a much longer stress relaxation time. Okay, so stress relaxation time roughly correlates with viscosity. You can think of it in the same way. All right, so, and the thing is that it increases continuously, but enormously. It just shoots up so that you can get a orders of magnitude increase in just tens of degrees. Okay, that's very typical, this incredibly fast increase. And so then it just goes out of range, right? It increases so fast that it goes out of range. You cannot wait long enough for it to equilibrate anymore. And on that, and if you can't wait long enough for it to equilibrate, it has fallen out of equilibrium, and it is a glass. That's what you call a glass. All right, so what are the phenomena, the collective phenomena that we want to understand? Let me describe those first. So you're going to learn, maybe you came here to learn about machine learning, but you're going to be forced to learn a lot about the glass transition too. Okay, so the idea is the following. If I'm at a high enough temperature, I just have ordinary liquid behavior. And what is that? That if I look at the relaxation time, it's what's called Arrhenius. The relaxation time goes like e to some energy over t, right? And what is that? That is an energy barrier, or free energy barrier, right? So that if there's a characteristic barrier size in this problem, right, then the Boltzmann constant tells me that the relaxation time, the probability of overcoming that barrier should go like this, okay? And so the relaxation time increases as I lower the temperature. If I look at how the stress relaxes in time, it's exponential in time. And it's exponential with that time scale, with that stress relaxation time. Okay? And if I look at the dynamics, they're spatially homogeneous. Pretty much everybody's doing this, you know. Anybody can rearrange at any time. Okay? There's not huge differences from one particle to another. This particle could be an atom, it could be a molecule, it could be a polymer, right? It could be any of these things. It could be a colloid, okay? A nanoparticle, it doesn't matter. Okay. Now I cool the temperature further, okay? Then I go through an onset temperature, and this is not a transition, it's just it's a crossover, okay? It's just a smooth change of behavior, and it changes into what I'm going to call a glassy liquid, and the way that's different is now the relaxation time is not Arrhenius. It's as if, as I lower the temperature, it's super Arrhenius. As I lower the temperature, it's as if the barrier it has to go over gets bigger and bigger. So it slows down much faster than you would have expected from the high temperature behavior. It starts slowing down. That's what I mean. The dynamics just shoot up. Okay, the stress relaxation time just shoots up very rapidly. They really slow down. Okay, the relaxation as a function of time becomes, with this time scale, it still depends on this time scale, but it becomes a stretched exponential. Okay, not exponential. And the dynamics become spatially heterogeneous. A very similar thing, actually, and it's not so different in terms of the physics, is traffic, right? If I have traffic that's way below jamming, low density, okay, then all the cars are more or less going at the same speed. There's some distribution, okay, but if you get close to jamming, though, you're stuck and the car in the next lane is going, right? That always happens. And so there's a big difference of mobility. Some particles can move a long way in a given amount of time. And what is that amount of time? That time is the stress relaxation time, is the right time scale to think about. So some can move a long way, others are essentially stuck, okay? And that difference becomes more and more pronounced as you lower the temperature towards the glass transition. Then finally, there's this glass transition, which again is not a transition. It's just when you can't wait long enough. Your stress relaxation time is now longer than your window for waiting, and you fall out of equilibrium. The dynamics are still spatially heterogeneous. And a cool thing here is that what the relaxation time is depends on how long you wait there. So if I quench from a high temperature to below the glass transition, and I look at the relaxation time, initially it's pretty fast, like it was at the high temperature. But the longer I wait, the slower it gets. Okay? So it depends on how long I have been there. So it's really out of equilibrium. Okay, so why did I do that? Oh, yes. Yes, so let's go through each of these things in turn. The relaxation time being Arrhenius. Yeah.
One question. Going back to what you said with the example with the car next to you going really fast. So then, in a glass, you see that behavior? Like
yeah.
In, for example, the glasses you showed in the video.
Yeah.
How can you see that? I mean, is it something that you can appreciate, like, you know, with your eyes, or how can you?
People do it in various ways in the experiments. Let me actually, I just realized since you ask, I have some movies. Okay, so you can do it either in simulations, okay, but experimentally people have done it with NMR, okay, and also with fluorescence recovery after photobleaching. Okay, so you can do this thing. You can see that kind of heterogeneous behavior appearing. So that has been established by those methods. This is actually a movie of a granular system. So this is a system of grains. Okay, they're on a wire mesh. So it's a two-dimensional system. They're sitting on a wire mesh, and gas is being blown. Turbulent gas is being blown through this, and because of the mesh it becomes turbulent, and the little eddies push the particles around, okay, and so they get excited, and at a high enough density, here's a movie of the particles, and they are colored according to how far they moved during the relaxation time, during the stress relaxation time, and you see that the blue ones didn't move very much, and the red ones moved the most. Okay, so you see that heterogeneity. Okay, yeah. All right. So let me just go through now. Let me just go through a little bit more quantitatively what I said earlier. So this Arrhenius to super Arrhenius crossover at the onset temperature. So if you look at for example, this is the log of the viscosity, but it could equally well be the log of the stress relaxation time divided by the glass transition temperature over temperature. So if this were Arrhenius, it would be a straight line. Okay? This is the log of the relaxation time versus 1 over temperature. If it's Arrhenius, it's a straight line. And there are some systems where it's sort of straight. Okay? Those are network glass formers like silica. Okay, like what's in window glass or something like that, or the glass vessels I showed you. But a lot of glasses are not like that. They are very, very curved on this. That's a super Arrhenius behavior, that the lower the temperature is, as you go this way, okay, the relaxation time just shoots up much faster than linearly. So that's a super Arrhenius behavior. And this is showing what happens at the onset temperature. This is a simulation. So at high temperatures, so this is temperature here, so at high temperatures, if you look at the relaxation time and extract this energy barrier, it's just flat. Okay? So there's a well-defined energy barrier. But below the onset temperature, that energy barrier just gets bigger and bigger. Okay? So the relaxation time is slowing down faster than you would expect. Okay? All right. This relaxation being exponential. So here is the relaxation function. So here is, I'm not going to go into what it is, but it decays, right, with time, and it decays on the scale of the relaxation time. And what you see is curves for different temperatures, okay? And if you fit it to this form with a stretching exponent, what you see is that at high temperature, that exponent is about 1. It's exponential. But as you go lower in temperature, okay, it drops, okay? It becomes stretched. And the temperature at which this drops is the same temperature at which you go from Arrhenius behavior to super Arrhenius behavior. That's the onset temperature, okay? And where the dynamics become spatially homogeneous, heterogeneous is the same temperature again, okay? So, what are we going to do with machine learning? What question are we going to ask with it? How are we, to look at these phenomena? Where do we start? Well, here's where we decided to start. So the whole point is, in ordinary liquids, any particle can rearrange at any time. What about solids? Well, let's think about crystals. Okay, what do crystals do? Well, it turns out that particles that are at certain defects called dislocations are far more likely to rearrange than particles that are in crystalline regions, okay? Either due to thermal fluctuations or to applied load. So then what about glasses, or what about glassy liquids? Are there certain ones that are more likely to rearrange than others? And can you pick it out from their structural environment? You see, in crystals, we can. Their dislocations are topological defects. We can find them, nice tools for finding them, okay? But in a glass or a glassy liquid, everything's a defect. It's disordered. Okay, so we can't use that. But is there some other way to identify which particles have a high likelihood of rearranging? And that's actually been something that people have been banging their heads against for more than 50 years. I think it's bond orientational order. No. I think it's the local energy. No. I think it's free volume, how much space there is around this particle. No. Okay. Nothing worked. Okay. And sort of by 2010, people had given up. And the reason why is, if you look at a snapshot, if you look at snapshots of the structure, okay, as you go through the glass transition, as I said, the dynamics can increase by 10 orders of magnitude, but the structure hardly changes at all. You cannot look at this and say, oh yeah, that's a glass, that's a liquid. Okay? There's no clear distinction. Whereas, of course, liquid to crystal, there's a huge change. You can pick that out very easily. So there's no structural signature. The structure doesn't change much. Okay? No structural signature of the glass transition has been found. And there's been no structural signature of the kinetic heterogeneities. Which ones are going to be mobile? Which ones are not? Okay? So, so that's what we decided to try. Could we find something with machine learning? And the answer is, it was easy. Not only could we find it, it was a snap to do it. Okay, so so that's what machine learning is for. It's designed to find very subtle correlations. Okay, and it's great at it. Okay, so so how do you do it? So I'm going to give you the general flavor. So the whole point of machine learning is you don't just use one quantity. Like if you want to look at a photo and say, yes, that is Julie. Okay, you don't just look at her nose. Okay, you don't just look at one feature. You look at all the different features, right? Many, many different features, and you look for correlations of them with the image. Okay, and so that's the idea. You don't. What physicists always do is say, I'm going to think about it very deeply, and I'm going to come with the one quantity that captures everything, and nobody could do that for the glassy dynamics. Okay, so we're not going to give up on that. We're going to just say, let's use a lot of quantities. Any one of them is maybe not that informative, but I'm going to put them all together and see what they do. And then the idea is you use a small subset of data, a training set, okay, to infer a linear combination of these quantities that correlates most strongly with the rearrangements, particle rearrangements, okay? That's what I want to predict, whether a particle will rearrange. And then I'm going to look at it afterwards and say, what was it that was important? Okay, so it's backwards from the usual approach. So what quantities that we use? So at the simplest level, okay, we use the pair correlation function G of R, which is how many neighbors, what's the density of neighbors at a distance R? Okay, so how many neighbors have their centers in a given little bin, okay, at some distance R. Okay, so that it's just that. Okay, and actually the theory of liquids is based on that quantity. It's based on the pair, what's called the pair correlation function G of R. So that's what we're going to use. Okay, so we're going to just count the neighbors in different distances. Okay, and each one, what's happening? Okay, each different distance, I'm going to call a different structural variable. So I have how many particles there are, okay, per unit area in this bin, blue bin, and then how many are them in the red bin, how many per unit area in the green bin, etc. Okay, and each one of those numbers is a different structural variable. Now the key is you construct, and I can do many of these. I can do 100 different values of the radius. Okay, so I just look. Okay, and I construct then this m-dimensional vector. So if I have m different structural quantities, okay, which are the G of R at different R, okay, I construct an m-dimensional vector where the components are the values of G of R at different R. In other words, I have on one axis, I put G of R at my first value of R. Second axis, G of R at the second value of R. Third is the G of R at the third value of R, etc. So I have a 100-dimensional space, or m-dimensional space, where m is large. Okay, and now for each particle, I calculate it, how many neighbors there are, you know, how many particles there are at each of these distances. Okay, and the structural neighborhood of this particle then is encapsulated by a point in this high-dimensional space. Telling me how many neighbors are there at this value, how many neighbors are at that value, right? That's a point in this high-dimensional space. So now, the next step is to have a training set. Okay, so the idea of having a training set is that I choose particles that are just about to rearrange. Okay, a bunch of particles that are just about to rearrange, and then a bunch of particles that haven't rearranged for a long time. Let's say the stress relaxation time. And for this then, I'm putting some dynamical information in my training. So I have to know that. So for example, I might have a simulation where I'm following all the particles, okay, and then I have to identify, oh, this one rearranged. Okay, I'm going to include it in my training set. Okay, or it might be an experiment. So how do we decide if it rearranged or not? What's a rearrangement? So I'm going to focus on this quantity. Okay, it's called d squared min. Okay, and the point is, okay, suppose this is my central particle I, and it has a bunch of neighbors j, and I can extend this neighborhood out to include many particles as I want. Okay, I'm going to take the displacements of all these particles in a time interval, short time interval. Okay, and I'm going to decompose it into an affine piece, okay, which is just, you know, and fluctuations around that. So affine is, for example, if I apply an affine compression, then all of the particles move in by a prescribed amount, as if it were just a continuum, okay, elastic solid. Or if I shear it, then they all shear according to that amount, okay? But of course, these are individual particles. It's not a continuum elastic medium, and so there will be deviations from that, okay? And the squared deviations from that best fit elastic deformation, or, you know, best fit affine thing, is this d squared min, okay? Divided by the number of neighbors I have, so per particle. Yeah?
Actually, I have a question from the last slide.
Yeah.
Trying to understand why are you trying this set of parameters by enlarging the radii around one particle and looking at the number of neighbors around it. Is it because it's just looking at the structure, or is it because of some long-range interaction between, or long-range response, let's say, between particles? What is the feature of the system that gives you this set of parameters?
Yes, so we're using something which has been known for a long time, okay? We made use of this to say the rearrangements, if you look at rearrangements on the microscopic timescale, they are localized. Okay, they're not extended across the whole system. And so that says to us, well, maybe then just knowing the local structure might be enough. And that's why we're looking just in the region around this particle, and we're not looking at something that's collective. If it were collective, though, we could have done it in Q space, in momentum space, right, in wave vectors. So it depends on your problem. In this case, we know rearrangements are localized, and so we're going to make use of that to define this a localized structural variable. Yeah.
So it's actually localized.
It is actually localized. Yeah. So we're going to use that. So I'm glad you asked that. All right. So the point is then d squared min, so if it's large, okay, that means there's a rearrangement. If it's small, then everything just sort of, you know, changed together. All the neighbors sort of changed together, okay, and it's not rearranging. So you can put thresholds on this, and I'm not going to go into those details. These are all in our papers, how to put thresholds on these, okay, to say what's a rearrangement and what's not a rearrangement. So if you go back to that, so then I have my training set. I have particles that are about to rearrange, particles that haven't rearranged in a long time. And I forgot to include something about how large does the training set need to be. And this is a very interesting thing about machine learning. So you need enough data. You need your training set to be large enough, okay, in order to get a good result. Then you would think, if I have too much data, that's a problem. I'm overfitting. And that should cause problems, right? In fact, that's a very interesting thing about machine learning. And, okay, I'm not going to go into it, but actually it flattens out. So if you add more and more data, it actually flattens out. It learns what it needs to learn, and then it doesn't actually go back down. It's an interesting feature of this. It's something that people, you know, there are various theories for this. You can actually understand it from the physics of jamming, which is how bubbles and grains end up going from liquid to rigid, actually. So they're actually, you can use, or glasses, you can use that kind of theory to understand why that's so, but I'm not going to go into that. Okay, I'm just going to say that, okay, so suppose we had these two subsets. And so now remember, each particle is a point. Their structural environment is denoted by a point in this high-dimensional space. And now I'm just going to color the points, okay, depending on which subset of my training set they are at. If they're about to rearrange, they're white. If they haven't rearranged for a long time, they're gray here, okay? And now what you do is you construct a hyperplane in this high dimensional space, so an m-1 dimensional plane that best divides between the two groups, best separates these two groups. Okay? That's called a support vector machine. It's the simplest, dumbest machine learning method. It was developed in the 1970s. Nobody uses it anymore for machine learning, okay? But that's what we do. And I'll talk about the advantages of this versus other methods. So that's it. We have this hyperplane. And now we're going to define a continuous variable, scalar variable softness, okay? Which is if I add a new particle that was not part of my training set, or a particle, whatever, any particle, I can take it and I can look at how far is it from the hyperplane. The distance from the hyperplane is the magnitude, and the sign is if it's on the rearranging side of the hyperplane, then it's positive. If it's on the non-rearranging side, it's negative. So that's it. That's my quantity. That's my structural quantity. So I've reduced the positions of all the neighbors around each particle. First, I reduced it to just counting the number in each ring, okay? And then I reduced it further just to the scalar variable softness. That's it, okay? So, and it works. So this is a simulation, okay, of a system that is above the glass transition, and we now have the two sides of the hyperplane. The soft side is red, the negative softness is blue. Okay, and then it's going to peel away, and it's only going to show the particles that are actually rearranging at any given moment. That's a very small fraction of them, and 90% of them are red. Okay, so it worked. And here's the distribution of softness. Okay, here's the distribution for the particles that are actually rearranging, and you see that that is quite a different distribution, and that 90% of it is on the soft side. Positive softness side. Okay? All right. So now I can say, it's quite interesting, if I look at the probability that a particle will rearrange that has a given softness. So I just count what fraction of the particles are softness S are rearranging in any given time step. Okay? So it's the probability for unit time. That probability of rearranging at a given softness turns out to be roughly exponential in softness. Okay, so this is the log of that versus softness. It's roughly exponential in softness. Okay. All right, so that's the first thing we do. There's actually a better way. So this way is wasteful of data. And the idea is that we want to apply it also to experiments. Okay, so not just to simulations where you can run long enough and you can get enough data. Sometimes it's actually hard, and even in a simulation, to get a lot of data when the relaxation time becomes very long, for example. Okay, but in experiments, generally, getting enough data is an issue. Okay, so the first method, I said the training set is rearranging particles or highly long-lived non-rearranging particles, right? So if I look just at, this is a plot of d squared min, that quantity, okay, for a particle in a given time interval where a particle rearranged, okay? There's one particle here that rearranged, changed its neighbors. Okay, and this is a plot of the whole system. You see that it is high nearby and it decays away far away. Why? Because on this time scale, which is short compared to the relaxation time, the system is essentially elastic. It's solid. Okay, and so if I have a rearrangement, that produces a strain that propagates out and decays as a power law. Okay, so d squared min is reflecting, it's big nearby and then it's falling off away. And what we're looking at here, the fact that it's decaying away as you go farther away, that's that power law. And that's dominating things. Okay, so what we do instead is to recognize that, well, there are lots of places here that could have rearranged that didn't. That maybe had the same structure as this particle here, okay, but they didn't happen to rearrange. Can we pick those out as well? And you can pick them out by looking at fluctuations of this d squared min. In other words, if I look at d squared min compared to its neighbors, compared to some neighbors, then ones that are locally larger, okay, are more likely to rearrange. So even though there's this background power law decay, okay, some of these might have moved further than others, than their neighbors, whereas others might not have. Okay? So I'm going to use that information, and when I plot this quantity, what it is relative to its neighbors, you see it gets rid of that power law, and what you see is there are lots and lots of particles here, okay, that had larger than displacements, non-affine displacements during this process than others. Okay? So now I can pick out local maxima and minima of this quantity. And the local maxima will be, so the local maxima of this quantity will be like the ones that rearrange. Okay? I'm going to use all of them. And local minima will be the other subset of my training set. Okay?
Sorry.
Yeah.
I have a question. What is actually the false positive rate of this method? So you can 90% accuracy predict if something is going to rearrange, but how often does this predict that something is going to rearrange and then it doesn't?
Yeah, that's actually very not good. False positive is not good. There are lots of false positives. And why is that? Or false negatives. False negatives.
Yeah.
Yeah. The false negatives, there are lots of particles that are soft, okay, but do not rearrange. And that's part of the physics. Because actually the probability that any particle that is likely to rearrange actually rearranges is low. So that's actually real physics there. So we don't look at that quantity. Okay.
Can we not include that probability here if we already know, if we already have some idea about the probability? Can we not include that in the model?
Well, we're trying to get an idea what that probability is by defining this quantity in the first place. Yeah. So yeah.
Basically, all of this dark region that you just showed on the slide before would be this region where the algorithm would predict that the particle would rearrange, and indeed they are prone to rearrangement, but for any given particle that's prone in this dark region, the probability is low.
Yes. Okay. So for this one, that's right. They can have a large d squared min, larger than their neighbors. Okay, without actually rearranging. And in this case, the false negative actually does mean something, and it is yes. I should say yes. For method one, the false negatives don't mean anything. Okay, but for this one, they actually do mean something, and it is low. It is again about 10%. Yeah. Okay, so it actually does do a good job on that as well. On local minima, it does actually predict, those as well. Okay. All right. So now. So that worked quite well. It works just as well as the first method, and it's much less wasteful of data. Okay, so we often use that. But actually, recently we've done even better, which is the following. So, right, we have said softness is some linear combination of our structural variables. I'm going to just call them phi I. Okay, G of R, different R. Okay, and we found that the probability of rearranging, as I said, is roughly exponential in softness with the prefactor that depends on temperature. Okay? And so it's like, well, then why do we have to decide, oh, this is above threshold, it's a rearrangement. No, it's below threshold, it's not a rearrangement. Let's just do linear regression on this whole quantity, on d delta squared min itself. Okay? So then we use all of the data. Okay, and what this suggests is that this should be exponential in the softness. So we're going to do linear regression on the log of this quantity, And we can see, and this is great, we don't need to use a threshold to decide whether a particle is rearranging or not. We don't, it's sort of weird to use a binary classification with a hyperplane and then turn it into a continuous variable by using the distance from the hyperplane. Now we don't have to do a binary classification. We're just doing a linear regression. We're getting everything. Okay, and as I said, it's now we're using d-squared min of every particle, not just the local maxima and the minima, but everybody. Okay, so that's even more efficient use of data than our second method. Now, you do this and you do linear regression and the r-squared coefficient is 0.2. You say, oh my God, that's terrible. There's nothing in here. Okay, is that true? No, because this is not the way to look at it. Okay. So how do you assess the accuracy, prediction accuracy across methods? Okay, so our goal is to predict rearrangements. So what we're going to say is, let's say we want to pick the global maximum in each configuration. We want to pick out the global maximum of d-squared min. Okay, so let's find the particle in each configuration with that global maximum. I'm going to call it particle I. Okay, and now I'm going to make a ranked list of the softnesses of all of the particles. And I'm going to see where does this particle I fall in that ranked list. If it's always at the top, then I have perfect prediction accuracy. I predicted the global minimum maximum perfectly every single time because it's at the very top of the list, and that gives me 100. That's 100%. So I put this ranked list on a scale of 0 to 1. Right? Okay, and now I calculate where it is on that 0 to 1 scale on that ranked list. Okay, and now I average over all configurations. Okay, and so as I said, 100% is perfect. Method 3 gives me 87%. Method 2 gives me 88%. Okay, so even though the r-squared coefficient is 0.2, you say that's terrible. But actually, it does a great job. It can actually predict where the global maximum is. Okay? All right, so that's really the method that we use nowadays. It's not the method that we used at first. And all of these things, you know, again, I'm telling you all of these things because for a given situation, you might want to do different things. Yeah?
So you said earlier that you didn't want to just come up with one quantity that determines if it's going to rearrange or not, but isn't essentially...
No, we want to come up. That's exactly what we want.
Okay, so you want to do that through machine learning? Not
through machine learning. Okay. Machine learning looks at all of these rather informative quantities, many rather informative quantity, and comes up with a really good one, which is a linear combination of those relatively uninformative ones. Exactly. Yeah. Yeah, that's the idea. So the machine learning has helped me to figure out what that quantity should be. Okay. All right. So that physics is then in what is the hyperplane, or the normal to the hyperplane, really, which is softness, which is, of course, what we're doing linear regression on. Okay. So that is what tells me the relation between the structure and dynamics, and we can look at it a posteriori. Okay, it's not a priori the way we usually do physics. It's after the fact we can look and say, what does it tell me? Okay, the cool thing about this is that for all of this, we didn't need to know what the particle interactions were. We just needed to be able to track the particles as a function of time, their positions as a function of time. And that's good because in experiments, if I wanted to do experiments on grains or bubbles or colloids or nanoparticles, okay, that are in this, doing this, I wouldn't necessarily know exactly what are the interactions between all the different particles, and it's quite sensitive to the interactions. Okay, so if I have a system that's somewhat polydispersed, a little bit polydispersed, the interactions are a little bit different, then I'd be screwed up. Okay, so I didn't need to know that. All I need to know were their positions as a function of time, and that with video microscopy tracking or whatever, confocal microscopy tracking, you can do that. Okay, and I will show you examples where we have done that then. All right, just want to run through some other things. So there are unsupervised learning methods. So what we did so far is called supervised learning, that we had to have a training set. Okay? You don't necessarily have to have a training set. So here's an example of an unsupervised learning where you don't have a training set. So I have all my points in this high dimensional space. I know that they're colored white and gray, okay, but I'm not going to tell anybody. Okay, I'm not going to tell this method. So the method is blind to that. Okay, what the method does is it puts springs, okay, connecting the position, the point corresponding to each particle in this high dimensional space to its nearest neighbors. Okay, so you do what's called a Voronoi construction. You find the neighbors that are closer to it than to any other particle. Okay, you put springs to all of those. Okay, and you take this spring network. And I didn't draw it very well. They should all be exactly the same spring constant, just different lengths. So they're all at their equilibrium lengths to start out with. Okay, and now you take this high dimensional space and you just smush it down into 2 dimensions, any 2 dimensions you want. Okay, just collapse it onto a plane. And you look at what you have. And now here it's white and gray, here it's red and blue, sorry. Okay, so the red here are what are white here, the blue are what are called gray here. So you color it after the fact, after you've done this, and you looked, was there separation or not? Okay? And what you see is that in 2 dimensions here, the red is in the middle, so, and then there are 2 blues, so there are 2 different kinds of hard particles. So that's sort of interesting. This is it gives you different information, whereas in 3 dimensions there is some separation here, just red and blue. Okay. But if I look at the probability of rearranging, if you look at the scale, okay, it's going it's changing by less than an order of magnitude. Whereas in the case I showed you before with the training supervised learning, the probability of rearranging, it changed by many orders of magnitude over the range. Okay, so that sensitivity is far more sensitive with training, with supervised learning than unsupervised learning. So unsupervised learning is a nice way to get some insight into things, but it's not actually, for us, a practical way to do things. Okay. Then you say, well, what about neural networks? That's what everybody uses to do machine learning nowadays. Why don't you do that? Okay. So it turns out that if you use a shallow neural network, so that's, in other words, in neural networks, you typically organize your nodes into layers. And then if you don't have very many, and then all the nodes within a layer are connected to every node in this layer is connected to every node in this layer. Okay. And then sometimes there's sort of crosstalk across layers, so this layer is connected to maybe this layer over here. If you don't have very many layers, then neural networks actually don't give you any better prediction accuracy than the simple, stupid thing of the support vector machine or linear regression. Okay? But deep neural networks can do slightly better. I will show you that in a minute, how much better they do. Okay, so an example is what's called ResNet. This is a deep convolutional neural network. So here are my layers. Okay, there are many, many, many layers, and they are connected so that, you know, across a few layers, and they can be connected forwards, they can be connected backwards. Okay, and this is what people use for image recognition. Okay, this is the sort of state of the art for image recognition. Okay, and then what we do is we just feed it images. So I just feed it images that are centered around, let's say this, my central particle is the particle that I want, okay, to learn. I want to, okay. I feed in all these images. I tell them these are rearranging, these are not rearranging. It's like cats and dogs, okay? And it sorts them, okay? And because it's going to just tell me, is the image in the rearranging class or is it the non-rearranging class? It just gives me something that goes, a softness that goes from 0 to 1. Okay, and if we take this thing and we compare it to the support vector machine, okay, the support vector machine is really, really fast. okay, compared to a deep neural network. In this case, why is it fast? Because I've already reduced the dimensionality from all the positions of all the particles just to these structure functions, the g of r, different r's. So that's a huge reduction in dimensionality. So here I'm using these structure functions. Here I'm using the actual images. Okay. They both can handle 2D. 3D, ResNet is no good. It doesn't actually do well with 3D images. There isn't actually a great way of doing, a really terrific way of doing 3D images. And so the support vector machine is actually much better. Polydispersity, though, is, if you have enough data, is much easier to handle with the ResNet does much better. Except that now, actually, we've learned how to handle polydispersity within so many different particle sizes. So if you have a continuous range of particles, distribution of particle sizes, how do you handle that with looking at G of R? We've now figured out how to do that. So we can, this is actually not so much a problem anymore. But you look at the improvement. It's not much. Okay. These are two different cases. So it's not a huge increase. It is a little better. But the huge disadvantage is that with the support vector machine, we can go back and say, what is the hyperplane? What is the normal to the hyperplane? What does softness mean? And in the neural network, we can't do that. There's no way of figuring out what to learn, what was important. Okay, it just spits out a number. So, so I think for physics, deep neural networks can be useful, but it's not obvious that they're always the best thing. Okay, so more generally, okay, we have used two different families. So this is the one I talked about, just how many neighbors there are at each value of r. We also have things that have bond angle information in it. So then you have three particles, I, J, and K, and look at the bonds in between, the angle of the bond in between them, and that sort of information. Turns out that for spherical particles or circular particles, okay, you can get 90% accuracy if you use 100 radial function and 22 angular functions, but you get 88% just forgetting about the angular functions, so we don't bother with angular functions. But if you're looking at another system, for example, we've done ellipsoids or dimers of particles, then you really do need the angular functions. Or for something like silica, which is a covalently bonded glass, you need it. Okay. The other interesting thing is, if I have an A-B mixture, which is the kind of system that all of our simulations are for the glassy part. Okay. If I have a central A particle, there are really two pair correlations that matter. I need to know how many A particles are there at every radius, and how many B particles are there at every radius. So if I have two different size particles. We use two different sizes because if you use all of the same size, they tend to crystallize. Okay? So people studying glasses on the computer usually use two different sizes. Okay? And so you need these two things. And just using the height of the first peak of this pair correlation function. So if I look at these pair correlation functions averaged over all the particles, there's a nice peak. Okay, first peak. And I look at the local G of R. Okay, for each particle, I can pick out what is that value G of R at that value of R, where the peak is for the average G of R. For GA and GAB, and just using those two numbers, you can get 77% prediction accuracy. It's actually not terrible. Okay, so it's really mainly the height of the first peak, and it turns out you can now go back and look at the hyperplane and say, okay, how many structure functions did you need? Okay, if I just have the height of the first peak, okay, just GAA, that's 64%. As I said, if I use two, GAA, the first peak of GAA and GAB, I get 76%. Okay, and then I just get a slow increase after that. Okay, so, and what are the important things? So you can look at the weights in the hyperplanes, which variables are weighted most strongly. By the way, if you look at any given variable, there's a distribution of values over all the particles. And before you do the support vector machine, before you fit the hyperplane, you want to normalize all the variances to 1, so that systems with it very spread out and systems that are very narrow distributions are on equal footing. Okay, otherwise, okay. So you normal. So, okay. So then I look at the weights of these, and I see that the weights are high. This is G of R, and this is the weight. So this is what the average G of R looks like, and these are the weights. And you see that it's large in magnitude at the first peak and at the first valley. Okay, and it gets smaller as you go further away. So it's just saying, so this, in the end, turns out to be the difference between soft particles on the soft side of the hyperplane. If I average over all of those, what does their pair correlation function look like compared to all of them? The difference is tiny. But what's the difference is that soft particles have a lower first peak and a higher first valley. What that means is that they have fewer neighbors surrounding them. Easier for them to get out. So there's this old picture of things rattling around in a cage. This is the cage. So this is a way of quantifying a very old idea in the glass literature, the idea of particles being trapped in a cage. This softness is telling you the strength of the cage. Okay. All right. I'll skip this. How am I doing on time? It is 8:40? What? 8:40. Okay, 5 minutes to the break. Okay. So, yeah, why don't we stop here and then, but come back, if you don't mind, come back 5 minutes early? Okay, so we still just take a 15-minute break? So we'll start back at 8:55 instead of 9 o'clock. So far, what I've shown you is that we've got this quantity softness. It predicts rearrangements. Excellent. It does a great job of predicting rearrangements. But so what? Okay? That's not our goal in life. Our goal in life is to gain understanding of the collective phenomena in terms of the microscopic physics. We haven't done that yet. Okay? So I've talked so far about the machine learning part of it. So in the second half, what I'm going to talk about is how to go from this quantity, softness that we have, and actually learn some physics from it. And I'm going to do it in some detail for this problem, and for a couple different problems. And the reason why I'm going to do that is because I actually think this is the hard part. Okay, so the first hard thing is, in any given system, what do you want to look at? What do you want to train for? And we decided that we were going to train for understanding the connection between structure and dynamics. Okay? Because dynamics is the glass transition, right? The glass transition is all about rearrangements. Okay, so that was sort of an obvious thing to do. But now we've got this quantity. How do we use it to make progress in learning physics? That is not so obvious. Okay, so we'll come back then in 15 minutes and talk about that. Any questions before we break? Yeah.
Yeah. So you showed this graph of structure parameters, and like if you have more of them, your prediction gets better. So it was kind of suggestive that the order matters. Like, does it matter if you which structure parameters do you use, or any two make a big increase, or do you have to start with GAA and then GBB and then we'll have a big increase?
Those are the ones that are most important. That's right. And you can do this thing called recursive feature elimination. One nice thing about the support vector machine in particular is that you can basically say, okay, let me take the structure function with the lowest weight, the one that mattered the least. Let me remove it and then train again. And then just keep doing that, okay, until you have fewer and fewer of them. And what are you left with? Yeah. Okay, and that is what you're left with is really the first. You can do really well with just the first peak of GAA and GAB and the first valley. So with 4 quantities, okay, you can get up to, what was it? 4 quantities, you can get up nearly 80%. Okay, and the rest of them, okay, they get you up eventually to 88%. Right?
So can you then say that the softness parameter is mainly linear combination of GAA and
Yeah.
GAV?
Yeah. So now that you have it, it's easy. And in fact, we've done another set of another system, which is jammed particles. So these are particles that repel if they overlap, and don't repel, and no interaction if they don't overlap. So they're like hard spheres, but they allow overlap, and the more they overlap, the more they repel. And if you take jam packings and you train on those, what you find is that all that matters, softness is really simple. It's just, I need to know the number of neighbors, Voronoi neighbors, nearest neighbors, that are overlapping, and the number, okay, and that's almost for almost all cases, that works, that's it, that's all I need to know. But also, if I'm at very low pressures, or very close to unjamming, okay, then you need also to know the number of neighbors that are gaps, that are not overlapping. Just those two things. So softness becomes incredibly simple. But you see, the nice thing about doing the machine learning and getting that out is then you can be sure that that's what it is. Okay, otherwise you're guessing. And the thing is, people only ever guessed one thing before. To guess a linear combination of two things was surprisingly something nobody had tried in 50 years. Yeah.
I mean, I'm not really an expert in this field, so maybe my question is a bit naive, but so you start with saying, okay, let's calculate the number of neighbors around a particle and use it as basically a variable to put into our machine learning algorithm. But what if I come with some other definition for geometrical structure?
Yep.
And my machine learning algorithm will say that it has much bigger distinguishing power between two types of particles, and now we'll end up with just another variable at the end.
That's right.
It's possible, right?
Yes.
But then you start, but how are you going to interpret this at the end? Because you try to interpret physics from the correlation variables that you got, well, from some correlations that you got. And I can choose another variable and get another correlation at the end, and will it actually influence at the end my physics and what I'm trying to understand? Yeah,
so it does, but you can say which one has a higher prediction accuracy, which one does better. And this is why we really did try to work to get our prediction accuracy to be as high as possible. Because then we had some confidence that this was telling us the physics that we wanted to know.
Yeah, but I'm saying more like the first step, like when you choose the most basic variable, did you try to do some other definitions of how geometrical structure?
Oh yeah, we tried a number of things. And in fact, a way to do this systematically so that you're sure you're not missing anything is to use persistent homology, which I didn't talk about, but you can use persistent homology. I'll talk about that tomorrow in a totally different context, but you can use persistent homology to try to be more systematic about what is the information you need to include and not include, and look at that. And yeah, so there are ways to do that. Okay, yeah.
I guess tacking on to that a little bit, so far the prediction accuracies you've got were really, really good, and it appears that you can get closer and closer to 100% prediction accuracy as you get better and better at predicting these quantities that should describe the system. But how sure can you be that everything is really encoded in the geometry, or how close do you think you can get to that 100% goal?
Yeah, it's very interesting that no matter what method we use, we can't get much more above 90%. So we've tried, I don't know how many different machine learning methods, maybe of order 8 or 9, 8 to 10 different methods. Nothing does better than about 90%. And so we might as well use a support vector machine, which at least we can understand. Okay? And I think there is physics in that. The fact that we really probably can't predict better than 90%. And what is that physics? Is the physics that it's not purely local? That could be. Or there's also the fact that there is there is stochasticity in the problem,
Yeah.
right? And so, for example, the lower our temperature is, the better the prediction accuracy. Okay, so as low as we can go, okay, we can get to then prediction accuracies closer to 95% instead of 90% at low temperatures, because temperature is not doing things, getting us over, high barriers, which, it shouldn't, which is gets more and more unlikely. So, so I think there's something like that in this.
So that's interesting. And the machine learning also gives you access to understanding what that extra bit of physics.
Yes, yeah, or it gives at least some hint as to where it might lie and that you could then check out, which we have not done yet. There's another question, which is, okay, well, I'll get to that after the break because there's something I haven't explained yet, so I'll explain that first. So, so you got this quantity, it predicts rearrangements, okay? Who cares? We wouldn't care, right? Unless we could use it somehow to understand glassy phenomena. And why? Because softness, if I have the softness of every particle, that's still a microscopic quantity. I haven't made that bridge to the collective macroscopic scale. Okay? And what does statistical mechanics do? It says, well, you can have particle-based quantities, but then you average them, right? You look at averages of them over the ensemble. Okay? And so that's where we started. It's like, does the average softness tell us something about some collective property? Is there some collective property that depends on this average softness, or that is correlated with it? And if it is, then there's hope. Okay? So, sort of exhibit A that people always use when they said, structure really doesn't matter for glassy dynamics. It's not structure. Structure can't tell you. Okay? Exhibit A was this system. So it's basically what you do in liquid state theory. So liquid state theory says, okay, you start out with a potential, which is, for example, our Leonard-Jones potential. So I have a short range repulsion and a longer range attraction, and then it decays to 0. Okay? And instead of using this Leonard-Jones interaction, the idea of the theory of liquids is that the attractions are there just to hold the thing at a high density so that the repulsions control everything. The repulsions determine the structure. Okay? So, so what you do is you cut this off at the minimum and then you shift it up so you get the repulsive piece of the WCA is exactly the same, right? It's just shifted up. Okay, but you get rid of the attractive piece. Okay, so you just have the repulsions that are the same as for Leonard-Jones, but you're missing the attractions. And you look at these two systems, and they have very different dynamics, very different glass transitions, okay? But they have extremely similar pair correlation functions. In fact, the whole idea of the theory of liquids is that the pair correlation functions are essentially the same. So then you look at this, well, then, okay, softness is based on the pair correlation function. How could it tell us anything about the dynamics? Okay, so we looked at this. And so here is the average G of R for the two potentials. So the red is the purely repulsive one, the blue is Leonard-Jones. You can see how similar they are, almost on top of each other. Okay, but here are the dynamics. Here's the relaxation time as a function of 1 over temperature. The blue is with attractions, the red is without the attractions. Okay, really, really different glassy dynamics. Okay, the relaxation time is a function of 1 over temperature. It's totally different. This is log of relaxation time versus 1 over temperature. A straight line would be Arrhenius. So you see it's not straight. In either case, that says in both cases, it's super Arrhenius. Okay, but it's initially straight, but below the onset temperature, it peels away and becomes not straight. That's super Arrhenius behavior. And now, so what does softness say about this? So these two systems are so similar that we were able to use the same hyperplane for both of them. And this is a nice trick. I don't know if it's useful for anything except our problem. But suppose you want to train over a range of different densities, a system over a range of different densities. Or you want to choose a range of systems, in our case, these two systems. Same density, but two different systems. What do? The key is in your training set to choose things from examples from the different densities or from the different potentials. So in fact, in our training sets, okay, half of the rearranging subset came from one potential and half from the other. And same for the non-rearranging particles. Okay, so we just used both potentials, and then we could use the same hyperplane, and it worked. Comparable prediction accuracy, very high for both of them. Okay, and so this is the average softness for the two systems. And you see that tiny, tiny change of the average pair correlation functions. The softness is just a weighted integral of the pair correlation function, right? It's a linear combination of the pair correlation different r's, so it's a discrete sum, okay, because it's been, but it's basically, you can think of it in the continuum limit as a weighted integral of g of r. So the average softness is a weighted integral of the average g of r. Okay? So the g of r's are very similar, okay? But the weighting is such that the average softness is really different for the two systems. So what softness does is it takes that tiny difference and it makes it noticeable, right? Because of the weighting, because it weights most heavily the parts that are different. Okay? And so the average softness is different for the two systems. And now I can plot the relaxation time. Instead of plotting it over 1 over temperature, this is the average softness as a function of 1 over temperature. I plot just parametrically, I plot the relaxation time as a function of the average softness. They're on top of each other. Okay? So that says that the relation between dynamics and structure in these two systems is actually the same. Okay? Because this is the relation between relaxation time and average and softness. Okay? It's actually the same in the two systems. What's different is the softness at any given temperature. Okay? So because these two things are the same, that is really telling me that the average softness really matters to the relaxation time. They are strongly correlated together. And that says, aha, okay, average softness, I'm getting now towards something that I would think about in statistical mechanics, the average of some microscopic quantity, not the quantity itself, okay? And it is related to a collective property, which is the relaxation time. Okay, so it does. All right. Sometimes I forget that I have my punchlines in here. Okay, so remember what we want to understand. The relaxation is exponential in time above the onset temperature. It's stretched exponential below. The relaxation time is Arrhenius above. It's not super Arrhenius below. The dynamics are spatially homogeneous above the onset temperature. They're spatially heterogeneous below. That's what we want to understand, just for starters. And I showed you this already, the probability that a particle of softness S is rearranging. Okay, so this is high temperature. So the probability of rearranging is actually not that sensitive to softness at high temperature. But what you see is that as you lower the temperature, it covers a bigger and bigger range. It becomes more and more strongly dependent on the softness. Softness is a better discriminator at lower temperatures than it is at higher temperatures. Okay, so now I can take this, okay, and remember the softness decreased as we lower the temperature. That's this plot, right? Softness decreases as I lower temperature, okay, not by much. But the probability of rearranging changes by several orders of magnitude. So it's a much stronger change of the probability of rearranging. So now, here is what enabled this to be so useful. Okay, if we look at the probability of rearranging as a function of 1 over temperature, same data as in the last plot, but now I take particles of different softnesses. So the red are in as the highest softness. Okay, the blue are at the lowest softness. So now I bin them according to softness. What you see is that for a given softness, the probability of rearranging is a straight line on this log versus 1 over temperature plot. It's Arrhenius. What that means is that particles of a given softness have a well-defined energy barrier for rearrangement. Okay, that is the key to everything, because that means that this is telling us something about the energy landscape. It's not just structure, it's telling us about the energy landscape of these things. Okay, and that we can extract that energy barrier. So the probability of rearranging, right, is e to the some sigma of s. I'm going to say some sort of entropic term which depends on softness, and then an energetic term that depends on softness. Okay, and I can plot these as a function of softness. And you see, right, high softness particles have low energy barriers. Okay, low softness particles have high energy barriers to rearrangement. Okay. And so then what is happening, okay, so there is a characteristic energy barriers, and it is this distribution of softnesses, or the fact that there's a distribution, not every particle has exactly the same softness, there's some distribution. It's the fact that there's that distribution, and therefore distribution of energy barriers, that is what's giving rise to heterogeneous dynamics. Okay. So if I look at that distribution, what does it look like? It's approximately Gaussian. Okay, it's skewed a little bit. And what does it do as a function of temperature? Well, as a high temperature, it's this. As I change the temperature, it shifts down. The whole distribution shifts downward. What's that saying is that, right, there are fewer and fewer softer particles as I go to lower and lower temperatures. And that is why the dynamics are slowing down. That if the distribution did not shift, I would not get this energy barrier that's increasing as I lower the temperature. It's because the average energy barrier, or the whole distribution of energy barriers, is getting higher and higher as I lower the temperature, because this distribution is shifting to the left to lower softnesses. Okay? You see the softness is spatially correlated on the scale of about a particle. Okay, so this is the range, the correlation function is a function of distance, and that gives a correlation length. Okay, and you put this all together, and what you see is that it's very natural. Particles of different softness have different barriers to rearrange, and they are spatially correlated at short length scales. Okay, with a short correlation length, and that is in fact a very natural description of spatially heterogeneous dynamics that's correlated on this short time scale, which short length scale, which is in fact what we saw in the movies. Okay, all right. So so that just falls right out. Now, let's suppose I take a system that is above the glass transition temperature and now quench it below the glass transition temperature. Then I said the behavior depends on how long you wait. So this is the waiting time. So initially, or at short waiting times, okay, this is softness. So now softness is on a red to black scale. So red is soft, black is negative softness, most negative softness. And it's also on a transparent, opaque red to black transparent, so that we can see a little better. Okay, that's a scale for softness. And what you see clearly is as you wait longer, it's getting blacker and blacker. Okay, there's less and less red in these pictures as you let the system just sit there and evolve as it ages. Okay, so the softness distribution is shifting to the left also as a function of time if I'm out of equilibrium, if I quench below the glass transition. And the thing about aging is that aging of glasses, oh my God, it's out of equilibrium, and so it doesn't just depend on our state variables. I don't just need to know the temperature and the pressure and the number of particles and that sort of thing, right? I need to know all about the history of how it's prepared. What temperature did I start out with? And then I quenched it to what temperature? And then how long did I wait? You have to know all of those things, which you don't need to know in equilibrium. In equilibrium, you only need to know the state variables in order to know the state of your system. Okay, here you need to know the whole history. Okay, so it's a little complicated. The point is that as I age the system, the relaxation time increases, okay, and the average softness decreases, okay. And if I do the same thing I did before, which is plot one, first let me do this. Let me look at this. Let me look at the probability of rearranging as a function of softness. So the high temperature points are the ones I showed you before, but I have now lower temperatures here, and these points are out of equilibrium. These are from the aging systems. And if I look at the probability of rearranging as a function of softness, this is a function of softness now at 3 different ages, okay, they're on top of each other. And what this says is that, in fact, the reason why the average energy barrier is increasing with the age and the relaxation time is increasing as a function of age is because the softness is shifting to the left. The softness distribution is shifting to the left. Okay? So, in fact, the energy barrier is increasing with age. The system falls into deeper minima. That's been the picture. But the point is that for particles of a given softness, the energy barrier is the same as it ever was. Whether I'm out of equilibrium or equilibrium, the energy barrier, the slope of this line, is exactly the same. And so what that says is that the reason why barriers are increasing is just because the softness distribution is changing, but the relation between structure and dynamics is still the same. And what that says is that aging is really a structural phenomenon. Okay, I'm just changing the softness. And it also says, what was I going to say? I'm starting to get tired. My short-term memory goes when I get tired. I was going to say something. Okay, never mind. Okay. Anyway, it's that. Oh, it says that all you need to know then, no matter, it doesn't depend on preparation history or age or anything. All you need to know is the average softness. You just need to, and your state variables. So you can just augment your state variables by one quantity, the average softness, and you know what's happening. Okay? So aging is not as complicated as people had thought. Okay? Once you introduce this softness. So that's nice. We're learning something. Yeah?
But doesn't that mean that you are not out of equilibrium then? I mean,
we are out of equilibrium because this average softness is changing with time.
But if the state of the system is described by just this, the state variables plus average softness?
But average softness is not a state variable.
Okay. So okay.
Yeah. So you just need to augment your state variables by quantity that is not a state variable, but just one quantity.
Okay.
And then that's all you need. Yeah.
Sorry, about the average softness, could you explain what does it mean if it is 0 or positive or negative?
So if it's 0, the average softness is right on the hyperplane. Right, it just tells you which side of the hyperplane it's on. Okay, but this depends on what hyperplane you choose. So if I train at different temperatures, I get different hyperplanes, and roughly they are just parallel to each other. Which is why, in fact, we can, for everything that I'm talking about, I forgot to say this, we just use a single hyperplane and we apply it at all the different temperatures. So, in fact, the prediction accuracy is highest at the lowest temperature that is accessible to us, that we can get good enough statistics at. So we actually train at the lowest temperature we can, and then we apply it to all the temperatures above. Okay? So, yeah. So then it has meaning. Then the average softness has meaning. Otherwise, if I have a different hyperplane at each time, at each age or at each temperature, then the average softness would not mean anything. So it's just saying something about the hyperplane that we happen to choose, and I would say it's not so much the value itself as the change of the value, how it changes with temperature, with time, or age, or something like that matters. Yeah.
So, yeah, I was going to ask, I think, along this line. So, am I going to conclude here that no matter what system has gone through, now I can just look at the local softness around in the system and then realize the parameters that I'm looking at. So are we going to exclude all the history, or is there interesting part in the history as well, like looking at the dynamics there as well?
So the point is, we don't have to look at all that history to be able to predict, for example, the relaxation time.
Yeah, but
yeah.
Is there any physical, even the dynamics of the system itself, is it given by this only local softness parameter?
Only average softness? Yeah, so there could be things that depend, for example, on the variance of softness or other things. But, and I'm not going to say everything just depends on the average softness. Certainly the relaxation time and you'll see other things that depend on that, only depend on that. Okay, so we are focusing on a specific set of phenomena here. Yeah. Okay. So remember, so this is this amazing thing that this is Arrhenius, and if I look at these, the dependence of delta E, the sigma, these two quantities that depend on softness and the probability, okay, they are roughly linear. Okay, so let me just take that seriously. Okay, so they've got some S0 minus S1s, and same for the energy barrier. Okay, and I'm just going to substitute that in. Okay, so I take that, I substitute that in, and I sort things out, and I get a piece, okay, that doesn't depend on softness, that's purely Arrhenius, and a second piece that is linear in softness. And this term is negative, so this overall is positive, and that's what I was saying before, that the probability of rearranging a given softness is exponential in the softness. Okay, so this is why this is where that comes from. So this is Arrhenius, independent of the local structure. This is the piece that depends on local structure. But look at that, there is a temperature when these two terms can cancel out. Okay, I'm going to call that T0. That's S1 over E1. And now I can go back and look. Oh, what was that thing that I just wanted to say? Let me just make sure it wasn't. Oh yes. I look at that and say, there's a piece where it becomes independent of structure. That's this. All these lines cross at a temperature. Okay? That's what I'm calling T0. That's really what that is. Okay? And now I can say, what is that temperature compared to the onset temperature that people measured other ways? Okay? From the super Arrhenius to super Arrhenius, or exponential to structure exponential. In fact, they looked at it from the crossover from homogeneous dynamics to heterogeneous, spatially heterogeneous dynamics. So they measured it by another way. We measure it from this. Plot them against the dotted line is where they're equal. They're the same. Okay? So this is the meaning of the onset temperature. Okay? The onset temperature, which is where the relaxation becomes non-exponential in time, non-Arrhenius in temperature, and heterogeneous, okay? That comes about because below this onset temperature, the probability of rearranging starts to depend on structure. Above it, I just have an ordinary liquid. Okay? Below it, it starts depending on structure. And clearly, right, the lower you go in temperature, the bigger spread there is in the probability of rearranging, the more sensitively it depends on softness. And this is why it makes sense to look at the lowest temperature that we can. Okay? So this is a really pretty picture, okay, that is coming out. We're understanding now physically a lot of this. Can we explain the exponential to non-stretch exponential relaxation? So now I have Arrhenius process. I'm going to look, one thing you can look at is, it's called the overlap function. It's just how far did each particle shift away from its initial position. And if it shifted above some amount, it's like half of the particle size, then you say it's 0. If it didn't shift that much, it's called 1. It's 1. Okay, and then you can average this over all the particles, and so it decays at short times they haven't moved, so it's 1, and then at long times they've shifted away by more than this distance, and it decays to 0. And you look at this decay, and now we say, okay, I have particles at different softnesses. They are all relaxing in an Arrhenius fashion. Let me just add that up. See what happens, okay? You get the dashed line. It's not very good. It gets worse as you go to lower temperatures. And it really doesn't capture the late time relaxation. So what's going on? So the point is that softness evolves even for particles that don't rearrange. Obviously, if you rearrange, you change your local structural environment and your softness changes, okay? But suppose you didn't rearrange, but another particle in your environment changed, rearranged, then your softness changes. So your softness can change even if you yourself are not rearranging, okay? And so if I start out, I just look at particles of given softness S. Here we just chose -3. I start out with a delta function of at -3, and I just wait over time, okay? And I just restrict myself to particles that are not themselves rearranging in that whole time. What you see is that delta function spreads out like a diffusion process and reverts to the mean softness distribution at long times. In fact, it's very similar to, it's almost a random walk, okay? And so basically what that's saying is that over time, hard particles tend to get softer particles tend to get harder, right? Because they're reverting to the mean, okay? Or they're reverting to the original distribution of softnesses. And you can work that out and say, okay, let me take that into account in my time evolution. So the time, I just say, okay, I am evolving in an Arrhenius fashion according to my softness, but my softness can change over time by this diffusion process, okay? And just solve that problem. This is called facilitation, by the way. That particles that don't rearrange, their softness changes due to other particles, okay? So other particles that are moved, that's facilitating their motion. So that's the physics of facilitation.
So,
yeah.
So this softness, local softness is changing, like is it a diffusion process?
It is, that's right. The softness of the particle itself is changing, and on average, it's as if it's a diffusion process.
So is it conserved then? Is like softness globally conserved parameter?
Softness is globally conserved. The average softness is constant at a given temperature if I'm in equilibrium.
So at a given temperature, if you age the system, the global softness is conserved?
If I'm just looking as a function of time.
Yeah.
Yeah. Right. Yeah. Exactly. So we can, so it's a diffusive process, and we just put that in. So it's a very simple theory. Again, we're not tracking each particle. We're just saying, oh well, I'm just going to assume that it makes a random walk each, and put that in, and that does extremely well. Okay, not only does it capture the time scale very well, but even quantitatively it works very well to describe that. Okay, so all right, so that we can get the non-exponential relaxation. So now the relaxation time itself. Okay, I showed you there was this relation between the relaxation time and the average softness. So let's just make a very simple assumption, right? We have these two pieces, the softness independent piece and the softness dependent piece in the probability of rearranging. Now let's just say, well, let's assume that the relaxation time is 1 over the probability of rearranging evaluated at the average softness. Okay? It should go like 1 over the probability of rearranging, and I'm going to just say it depends on the on average. It's just the average softness. So you take that, you stick that into here, right? You work that out, and you see that the relaxation time is exponential in the average softness now, with a coefficient here, which should go like 1 over the onset temperature minus 1 over the temperature. Okay? And now I can look at the aging systems. In the aging systems, the relaxation time is increasing with time, and the average softness is decreasing. So each aging system is following along a different trajectory. And each trajectory here is for a different temperature that I'm quenching to. okay? And I can pull out the slopes of these lines, okay? It should go like 1 over t0 minus 1 over t. I can plot that as, okay? And this is what I would expect from this expression. This is what I get, this is what I expect from the expression. This is what I actually get from the slopes of the lines. It works really well. Okay, so this is a very simple picture for the relaxation time as a function of average softness. Okay, so it predicts the relaxation time. And we actually, we have some experimental confirmation of this. So we applied this to colloids. Colloidal systems, just do video microscopy, 2D system. This is with Arjun Yod's group at Penn. Okay, and what you see is that, and just say, here's the average relaxation time as a function of softness, and it is exponential in the softness, as we find in the simulations. Okay, so this seems to be working. All right, so now we understand that these three things. Relaxation time is Arrhenius above, where softness doesn't matter. Then it starts to depend on softness. It becomes super Arrhenius. Below the glass transition depends on the age, and we understand how it depends on age. So now let's think about this a bit. Okay, I have the softness independent piece, and I have the softness dependent piece. Okay, if I'm sitting at a given temperature below the glass transition and just aging, okay, what's changing is the softness. This piece is not changing. So this is constant with age, but this term is changing. And that's why the relaxation time is changing. Okay? Is there some way that I can change this piece without changing that piece? So we thought, oh, well, what is this piece? Okay? Where does it come from? And one thing that would not depend on age, okay, there would be, I can think of this, there are two contributions to the energy barrier. There's this contribution that depends on softness, but then there's this contribution that doesn't depend on the softness. Where does it come from? So we thought, well, maybe there's a simple physical picture that says if a particle rearranges, it gives rise to some strain that propagates outwards, right? That it exerts strain on its surroundings. And at short times, I have basically a shear modulus in my system. It's a solid at these short time scales, okay? And so to exert that strain costs energy. Maybe that's the energy barrier, okay? So we thought, let's look at thin films of glasses. Because if I'm in a thin film, then how big that energy barrier depends on how close I am to the surface of the film. Right? It gets smaller. It should get smaller. That energy barrier should get smaller as I go to the surface of the film. And that would be a way to change this piece. And let's see if this piece changes. Let's see what happens. Maybe the softness changes too, though, as a function of. So we thought thin films are an interesting problem. And technologically, they're interesting because it turns out that you make glassy polymer films, plastic films, and you should be well below the glass transition. They should be solid, and actually they break. They pull apart because because they're thin, their glass transition is actually a lot lower. And so they actually act like liquids. So the thickness of the film really has a big effect on the dynamics, and it's a barrier to applications of thin films. Okay, so we looked at thin films, and this is 1 over the relaxation time. Okay, is the purple or the red. It doesn't matter. I have 2 different measures of it. And so this is the center of the film, and this is going to the edge of the film. Okay, so now the black line here is the density difference between the center and the edge of the film. And so what you see is that the density difference is 0, of course, at the center of the film, but as I go to the edge of the film, it changes. The edge of the film has a lower density. Okay, so this is the density at the center minus the density at where I am. And so this is where the density falls off. So that's where the surface of the film is. This tells you where the edge of the film is. Okay? This is the relaxation time. Okay? And so you see that as you go towards the edge of the film, the relaxation, 1 over the relaxation time, the relaxation time gets shorter and shorter and shorter. Okay? The dynamics speed up as I go to the edge of the film. What about softness? Now, softness is defined in a neighborhood, so my neighborhood, if my neighborhood gets to be outside of the film, then that, of course, changes softness a lot. And that's what's happening here. Okay? But until I get to the point where my neighborhood gets outside of the film, okay, it is flat. It's not changing. Softness does not depend on position of the film. In fact, the structure, this was a huge shock. Okay? I can use just an extremely general set of structure function and just ask, can I tell which particles are at the surface and which ones are in the bulk of the film? Can I tell? I'm just going to train on that, not worry about dynamics. Can I just tell where I am in the film? No. If you just look at structure, you cannot tell where you are in the film. It's just flat. Okay? So structure is the same until you get really close to the edge of the film. And so that's saying the dynamics are changing without the structure. Okay? And so then we can do the same thing. We can look at the structure-independent piece, the structure-independent, pull out the Arrhenius thing. Okay? And what you see is that the structure-dependent piece is totally flat. Okay? But the structure-independent piece, that is what is changing. And it's changing on the same length scale as the dynamics. Okay? So it says the surface is affecting the structure-independent piece, not the structure, and it's lowering the barriers for the structure-independent, purely Arrhenius process. That's actually consistent with the experiment. That's been established by the experiments, that it's a purely Arrhenius process that is speeding things up at the surface. And you know, we think maybe it is really the elastic cost of a rearrangement. That's what we're testing quantitatively now. So I hope in a month we'll have an answer to that. Okay, both for simulations and experiments. Okay, so that says 2 contributions to the variant. One that depends on local structure, and the one is maybe just the cost of a rearrangement. Okay, how general is this? I showed you one system, or 2 systems, Leonard-Jones and the Weeks-Chandler-Anderson, the Leonard-Jones, which is the repulsions. Okay, here's a totally different system. This is a model of silica, which is a network-forming covalently bonded glass. Totally different. Okay, here I have a very different distribution of softnesses than for the Leonard-Jones case. This is what's called a strong glass former, so it's nearly Arrhenius. This is very super Arrhenius. Okay, but if I look at the probability for rearranging as a function of softness, it's still Arrhenius. I've got that again. Okay, and if I now say, and here what people measure is the diffusion coefficient of oxygen atoms. That's typically what they measure. Instead of relaxation time, they measure diffusion coefficient. And so we just make this same assumption. We say the diffusion coefficient should go like the probability of rearranging at the average softness. Put that in. Okay. The points are the measurements of the diffusion coefficients, and the curve is our prediction. It's beautiful. It really works. Okay, so we can predict the relaxation time in this system. And silica actually has what's called a fragile to strong transition, so that at higher temperatures, at really high temperatures, it's Arrhenius, and then it becomes fragile at intermediate temperatures, and then strong or super Arrhenius at intermediate temperatures, Arrhenius at sufficiently low temperatures, and we get all that. Okay, that all comes out. Okay, so yes, really different system, and it still works. So we can cover the whole spectrum from strong glass formers to fragile glass. You know, it seems to work. All right, so we're really happy with that. Okay, that's glasses. But now, can we push this further? How general is this? So I said, okay, what about crystals? Can we apply the same idea to polycrystals, polycrystalline systems? So people talk about grain-bounded dynamics. I mean, the theories for crystals are incredibly complicated because there's all these different kinds of defects and screw dislocations, blah, blah, blah. Okay, and they do different things. And okay, So we said, okay, can we just apply this to polycrystals? So we took my colleague David Strolowitz and his student Spencer Tracy had simulations of 58 million aluminum atoms. They're really serious. We joke around, but they're serious simulators. And so we took their simulations and analyzed them. Okay, just calculate the hyperplane, did all that. So this is the standard picture. This is just a slice through the 3D crystal, a small section of this, okay? I'm not showing you all 58 million slice through the whole system, okay? But you see the grains, so these are crystalline grains separated by grain boundaries in the system. And this is the standard just measurement of crystalline order. This is softness, okay? So you see softness is really low in the crystalline regions and it's higher in the grain boundaries, but it's not uniform. It's not like every particle in the grain boundary has the same softness. And they're cool things, you know, there are certain things that are not crystalline, but they're not soft, okay, and so forth. There are various things you can say that are interesting for people who look at polycrystals and think about dislocations and grain boundaries. Okay, I'm not going to get into that, but let me look at this system. Oh, what was I going to say? Yeah. Oh, what this says is that, right, since we can do this and we can pick out the grain boundaries, we find that the soft particles are in grain boundaries and so forth, and that certain vacancies that we know are not important from polycrystals are not soft and so forth. That's saying that softness, we can apply this idea of softness not only to disordered systems, but we can apply it across the whole spectrum from order to disorder. Okay? So it's a generally portable quantity. All right. And if I look at it, it's Arrhenius in polycrystal. The probability of rearranging is Arrhenius in these systems too. Okay? And we can extract the distributed energy barriers in the system. It actually agrees with what people have done before, okay? And it tells you that grain boundaries actually look a bit like glasses. They're not the same. There's no onset temperature, for example, okay? But they do have this similarity, that there's a range of softness. Okay, then when we start saying, okay, what about epithelial tissues? So I'm on a cancer grant, Physical Science Oncology Center at Penn. Turns out that the stiffness of your liver is an incredibly good predictor for whether you're going to get liver cancer 7 years down the road. Better than any other marker for any other cancer. Okay, and you can get it from a simple ultrasound measurement. So, and then the question is, oh, does cancer come from stiffness differences, or is that just a side, it just correlated with it, but not actually a cause of the cancer. So, we're thinking about that. But it turns out that, so there are epithelial tissues throughout your body, for example, the lining of your gut. So epithelial tissues are tissues that are one cell layer thick and that sort of wrap around organs and so forth. And so that your gut lining, for example, is an epithelial tissue. And because they're one cell layer thick, they're rather fragile. They turn over very quickly, okay? And so they're constantly being replaced, and therefore they are susceptible to cancer. 85% of cancers originate in epithelial tissue. Okay. And recently, someone who worked with me as a postdoc, Lisa Manning, did something really cool, which is she showed that a very simple model of an epithelial tissue actually predicts the rigidity transition in these tissues quantitatively. Okay, so here's a movie. These are bronchial epithelial cells. Okay, and you can see them. These cells, they are moving, they're migrating, and there's some are rearranging around each other, some are moving together as a flock. Okay, and basically what we would want to do is look at movies like this and be able to predict what is the probability of each cell in this tissue to rearrange, to migrate. Because if a cell, if the DNA mutates and it becomes dangerous, okay, it doesn't actually do any damage if it's just sitting there. It has to migrate for it to be a problem. for cancer, okay? So we would like to know what's the propensity of each cell to rearrange. Can we do that with the same softness analysis? We just say, okay, we're just going to do the same thing that we did, and we're going to do it we'd like to do it on experiment. In fact, Indrajit just this week has done it on experimental data, and he finds that the prediction accuracy is 68%. Okay, not as good as for the other systems, but there is a complicating factor, which is that there is cell proliferation in the actual tissues, so cells are dividing. So given that that's happening, some cells are dividing, some cells are dying, okay, and disappearing. Those are things that are not taken into account in the softness analysis yet. Given that, a 68% prediction accuracy is respectable, okay? So, but meanwhile, we tested it on a model. So this is the vertex model. Okay, so the idea is there's some energy. What does that energy mean? We don't really know, but it depends on, it's the sum over all the cells in the system, and there's a term which says that cells like to have a certain perimeter. And if the perimeter of the cell is different from that, I pay a cost, like a harmonic cost for that, okay? They also like to have a preferred area, okay? And that becomes they're one cell layer thick and they want to have a preferred volume and the thickness doesn't change. Okay, so the area of the cell, if I'm looking down on this tissue, it has a preferred area and there's a cost for changing that. Okay, so you look at this and well, really the only thing that matters is the ratio of the preferred perimeter to the square root of the preferred area. It's called the shape index. So you know, you can work out what it is for a circle. 2 pi, something that depends on 2 pi or 2, whatever. Okay, okay. And here's the cool thing. That's Lisa. She was not my postdoc. She was a postdoc at Princeton. She had a fellowship, but she ended up working with me, and she developed the first attempt at softness, which is based on low-frequency modes, very cumbersome, and the machine learning method just blew that away. Okay, but that's what she did. And as a postdoc, so it's the first thing that showed that there was something that you could predict about rearrangements. Anyway, here's the vertex model. Here's the function of the shape parameter. So what it predicts is that if my shape parameter is bigger than 3.81 approximately, okay, the system is fluid and it becomes rigid at a preferred shape parameter of 3.81 and it's solid below that. Now that's if the cells are just sitting there. If the cells can propel themselves, okay, they have some self-propulsion, and then that shifts the transition and, you know, but you can get the salt more or less sort of glassy regime here or jammed and unjammed there, okay? And the amazing thing is that it works quantitatively. That they look at bronchial epithelial tissues and they showed that they're fluid until the shape parameter reaches 3.81 and then it becomes rigid. It actually predicts the position of the transition quantitatively. Not only that, if you look at the variation of the standard deviation of the aspect ratio of the cells, the aspect ratio, and you look at the average aspect ratio, okay? What they found was, this is the prediction of the vertex model, okay? This is experimental data, okay? Now, this corresponds to where it's jammed, it's fluid. And as you go this way, it gets solid. As you go in this way, it gets more and more fluid, okay? And what they found was over time, as these cultures mature, they rigidify and they go that way, okay? So, and so it really is described by that. And this is Jeff Fredberg, experimentalist at Harvard. Yeah.
Short question. So, as far as I know in these vertex models, to have this confluent tissue, when the cells grow, they have to be linked with each other somehow, when they run into each other?
Here, the packing fraction is 100%. They occupy all of the volume.
Yes, but when they run into each other, they somehow the vertices or the beads have to be linked to the neighboring.
That's right. It's all coupled together through this energy, through the Hamiltonian.
how, well, I would guess that at some point it would be a very important parameter how strongly two neighboring cells are cross-linked with each other.
So what goes into this, I didn't talk about this, but what goes into this coefficient, okay, is it's a competition between cell contractility and cell-cell adhesion. Mm-hmm. Okay, so changing those things actually changes this coefficient here.
Okay.
Okay.
But would not that be like cell-cell adhesivity? Wouldn't that be? I would have thought that would be a very strong parameter determining the fluidity of
yes. Yes.
But in your, so it never appears in these phase diagrams.
Yes. At zero propulsion, it doesn't affect anything, but it affects where this is.
So the propulsion depends on that.
Self-propulsion is, if I add self-propulsion to this, then the shape of this curve depends on adhesion versus contractility. Okay. It depends on that coefficient. Okay. Yeah. But this point does not. Okay. So here's the really cool thing. I'm telling you, this is not my work. This is Jeff Fredberg's experiment. He did bronchial epithelial tissues. They did Drosophila during development, during the process of gastrulation. They have different kinds of cell cultures. They have cancer cell lines. Okay, you put them all together. Okay, all of these follow along. This is the vertex model. It's the gray line. They all follow that. Okay, and just to show you, they're really different systems, and they have different interventions for how they jam or unjam, but they have this common behavior. And just to show you the Drosophila movie, so this is during the process of gastrulation. You see the system moves that way. It unjams, okay, during development. Okay, all right. So can we predict it? And yes, I'm not going to go into this. We're running out of time. It turns out this is the amount of information that you get from softness. You gain a lot if you're in the solid regime. As you go further into the fluid regime, you lose information, so softness is not that predictive if you're too far into the fluid regime. But look at this. The probability of, if I take a thermal version of the vertex model, it's Arrhenius. The probability of rearranging is Arrhenius. If I take the self-propulsion version, I can define an effective temperature depending on the V squared and the rotational diffusion of the cells. Okay, and the drag. So you can, and that works pretty well in the solid phase. It breaks down. The effective temperature description breaks down as you get to higher self-propulsion. But again, it's Arrhenius in this effective temperature. So it's really, this seems a very, very general result. Why? We do not understand, and we would love to. Okay, so I'm going to skip the last story, which is the story of plasticity. Just to show you that we looked at systems from covalently bonded silica to 2D colloid experiments, 3D colloid experiments, simulations of Leonard-Jones, simulations of polymers, and grains, experiments on grains. And all of these things, we analyzed softness, okay? And we found that the range of correlations for softness, okay, divided by the size of a rearrangement was 1. Across all these systems. And that says the reason why rearrangements are localized in these systems, okay, is because the softness is correlated on the scale of a particle. It has short-range correlations. That's why the rearrangements are localized. Okay, so so that was one thing, and the vertex model actually falls right on there as well. What did I get? The yield stress turns out for disordered systems. We looked at 13 different systems, I think, spanning, many different systems spanning 13 orders of magnitude in the elastic moduli. So really different systems, okay? And they all had the same yield stress, roughly, about 3%. And that corresponds to a change of the softness. How much does the softness have to change at the yield stress? That is roughly the same for these different systems. So softness actually tells us something about about the yield. Okay, I'm going to skip all of this because we're running out of time, because I'm just going to sum up. We can say a lot about, this is very cool stuff. All right, I'm just going to get back to I'm just going to sum up now. So, so I said machine learning is a natural approach to the too much information problem. That's what it's designed to do. It's designed to do dimensional reduction. Okay? So that says, okay, if I can't use statistical mechanics, machine learning, that's a logical thing to try. Okay? It's also really great at finding subtle correlations that traditional physics approaches miss. We showed that in the glass case. It could find it. Okay? And at least in this case, this machine learned softness is, I think, really promising as a basis for a theory. Okay? And what I didn't get to show you is how we are developing a theory for plasticity, and the next step is to apply to thermal. Thermal systems are a little harder, but I think we've got a clear path forward to develop a phenomenological theory, okay, based on softness that then has predictive power. Okay, so that is the goal here. So we are excited about this. I think there is just tremendous opportunity to learn new physics, to basically bridge this gap. Okay, and that's it. Thanks very much. So, questions? Yeah.
So this hyperplane, the weight, so the hyperplane defines a softness that can be seen as a sum of weighted pair correlation.
Yeah, it's basically an integral, a weighted integral of the pair correlation function, which then, you know, you could do theories on that. You can do sort of liquid state type of theories.
Yeah, so these, but the meaning of the weights, like, that's the next step, right? Like trying to understand if there's some way to extract these weights somehow mysteriously from this whole data.
Right, that's right. So sort of generalized mode coupling approaches, okay, which relate then dynamics to structure, could be used to try to then say, okay, well, this, given that we know that the relaxation time, for example, is exponential in this average softness, then that could maybe tell you, that might be able to give a theory for what the weights are, which could then be compared with what we get.
Yeah. It's really exciting.
Yeah. So, I mean, I think there's a lot of room for theoretical work that's opened up by this. Yeah. And that was the nice thing about choosing to use the pair correlation function, was then we could make connection to those kinds of theories in a very natural way. Yeah.
So here we looked at a system out of equilibrium and tried to extract a parameter that, given the system at this moment, I can predict what it will move to the next step, if I understand correctly. I was wondering how general it is, because we have many systems out of equilibrium, from chaotic systems, turbulent systems. So how general are this sort of approaches can be? Can I apply to any non-equilibrium systems, or any sort of barrier is still there?
Yeah, so I don't know how general it is, but I do know that basically it seems to work for any system that can be described by jamming. So jamming is something I've worked on for 20 years, okay? And it is, if you just take a bunch of spheres that, as I say, if they don't interact, they don't overlap, and if they overlap, they repel, okay? Then you take a system like that, 0 temperature, there is a density at which they are forced to overlap, above which they have to overlap. That's the jamming transition. And we spent a lot of time thinking about that. Now, if I take this system, if I take that system and I add friction, I've got a granular particle, and I maybe change the particle shape. If I add thermal temperature to it, I've got a colloidal system. Okay, if I've got if I maybe add attractions, then I've got a Leonard-Jones system. Right? So you can take that system and you can just add different things, okay, and it becomes a good starting point for thinking about all those different systems. And we sort of worked out over the years, you know, if you add friction, as that, a lot of that work was done at Leiden actually by Martin van Hecke and Wim van Saarloos's group. If you add friction, how does that modify this whole picture? If you add long-range attractions, how does that modify this whole picture? All these things. If you add these various things that make it into different realistic systems, what do you get? And this, just exactly this thing, machine-learned softness, defined this way, very specific thing, seems to work very well for all of those systems. Okay, now, but that's only a very small subset. Still, that's a lot of systems, but still a very small subset of all systems that are far out of equilibrium. I would love to use this to look at turbulence. I've been waiting for somebody to visit me on sabbatical, and it keeps getting put off, okay, who's an expert on turbulence, because turbulence is another far from equilibrium problem that has resisted physics. And one of the really puzzling things is to try to find correlations between, you know, coherent structures and energy cascade and so forth. I think this is, machine learning could maybe be used for that, right? So there are a bunch of different problems where I feel like, okay, you know, machine learning could be useful for this, you know, in different ways for these different problems. So, but of course, there are many other problems, and I have no idea of how general it is. But it's certainly a place to start. At least it's a starting point for thinking about things. Yeah.
Could you go the other way around and instead of going from the microscopic, you investigate the macroscopic picture and deduce from that the macroscopic properties? Could you feed into the system the macroscopic properties you want and deduce from that the macroscopic properties the particles need to have to create such a system?
Yeah, so there are a lot of people who try to do that. Like they try to learn TG, the glass transition temperature, by feeding lots of data about different systems. Or fragility, or you know, things like that. What was the example? It was an interesting example. I forgot. And I think you can do that. In fact, I'm really blanking. Okay, so I was talking to somebody, I was visiting someplace giving a talk, and they were telling me what they were doing, and I forgot what they were doing. But it seemed tailor-made for trying the same thing we did, because they could do a binary classification, but what they really wanted was a continuous variable. And you know, I remember suggesting, well, try the binary classification, because you might be able to use the distance from the hyperplane as your continuous variable. It seemed like it would work for that. And it's terrible that I cannot remember now exactly what they were doing. But I think there are cases where you can do that, and that can be really useful. Yeah. I think everybody's pretty tired, and things start early tomorrow. So thank you guys very much. You're a fun group to talk to, and great questions. So I really enjoyed it. Thank you.
Thank you.